Good day, everyone. We're reviewing Wetzel's Limnology textbook, edition number 4, and we are looking at chapter 7, The Fate of Heat, and more specifically today we're going to be looking at warm polymictic lakes. And before we do so, let's look at figure 7-37, which presents the thermal structure of warm monomictic Lake Victoria in East Africa. So on the x-axis, we have month as well as years here. And then on the y-axis, we have depth in meters. And so then we have these isotherms curves that are presented. And we have the presence of a thermocline in that time period, for example, in the May-June time period 1994. We also have a presence of seasonal thermocline in 1995 between the time of February through April, May, and that reproduces right here in 1996 as well. And they were saying in the text that full water column mixing occurs during the southeast monsoon when winds are higher over East Africa. Winds increase beginning in May, and depending on the phase of the El Nino Southern Oscillation, may remain elevated into August. And so therefore, what they're saying is that during that time period between May and August, we may have some amount of diffusion, some amount of turbulence that occurs where the waters are mixed and due to the influence of the wind, and we may have a tilted thermocline during that time. Which seems to be a bit, about the case here. We have like a thermocline that has developed in this area here with September, October, November time period. And then that's probably about it for this warm monomictic lake. Why don't we look at now the warm polymictic lakes? Lakes with frequent mixing to the near bottom and in which ice cover does not form are called warm polymictic. Diel stratification and mixing is prevalent in shallow tropical lakes. As observed for cold polymictic lakes, high-resolution instrumentation indicates that the near isothermy at a measurement site over Diel cycles may be due to wind-induced thermocline tilting, with stratification evident on the relaxation of the wind. The use of multiple thermistor arrays aligned in the prevailing wind direction and three-dimensional hydrodynamic modeling have confirmed this perspective. More persistent stratification is found in deeper Clear Lake, California, and the mixing regime of tropical floodplain lakes vary as a function of water depth. Polymixes can also be induced in shallow lakes that stratify during warm periods, but in which intermittent high discharge events replace a considerable portion of the lake water, and by geothermal heating in shallow lakes such as Lake Rotorua in New Zealand and in caldera lakes such as Ruapehu Crater Lake in New Zealand. So this is spatial variability. So this is figure 7-38, spatial variability of thermal structure at 3 stations within warm polymictic Lake Paranapitinga in Brazil. And so the first thing is we have, let's see here. We have 2 being the mid-lake station, 3 a more inshore station, 4 a more northerly station closer to the location where water from the Amazon River flows into the lake. This lake is part of the extensive Lake Grande de Curay at high water. Sites are several kilometers apart. The upper panel illustrates the Monheim-Obuchov length scale divided by the depth of the activity mixing layer, LMO over H, for station 2. During heating and light winds, positive LMO over H, it transits towards 0. Strong diurnal thermoclines form in the day as an DOY 181, with buoyancy frequency reaching 60 cph. In contrast, when winds are high during heating, LMOH divided by H is greater than 1, incoming heat is mixed deeper in the water column, DOYs 184, 186. So x-axis, we have the DOY, which is the day of the year. Here we have this this Monin-Obukov length scale divided by the height. And then we have the height with the temperature. Then we have the depth in meters, as well as the depth in meters here. And this is for station 3 and 4. And this is for station 2. So let's see. In both cases, the stratification that builds up in the day is eroded by cooling. At the onset of cooling, conditions were windy. LMO divided by H is less than -1, and the diurnal thermocline deepened as it cooled. For much of the night, -1, so LMO divided by H is between -1 and 0, which indicates wind mixing near the surface and mixing by convection throughout the actively mixing layer, as in Balbina Reservoir. The upwelling of cold water in the morning at station 2 and 3 indicated the thermocline had tilted at night, as in Lake Joanaka, and the lake had not fully mixed despite the near isothermy at the measurement site at night. The persistent near isothermy at station 4 resulted from the greater mixing associated with the incoming river water. So here, what they're saying is like, we have really good isothermy, and that is because that station is heavily influenced by the incoming temperature of the water coming in from the Amazon River, where it's not the case for station number 2 and 3. So that's pretty much what's going on here. Why don't we move on then? More persistent stratification is found in deeper Clear Lake. We already went through that. Meromixis. Lakes that do not undergo complete circulation are termed meromictic. In meromictic lakes, the upper layer, which periodically circulates, is called the mixolimnion. The deeper monimolimnion does not mix with the overlying water. The two layers may be separated by a thermocline or by a chemocline, where solute concentrations increase rapidly. The density gradients, be they due to temperature alone or the combination of temperatures and solutes, are called pynoclines. Meromixis develops as a result of conditions leading to chemical stratification, or when the depth of mixing possible from wind and cooling is shallower than the depth of the lake. Nomenclature describing meromixis was developed by Hutchinson, etc. Ectogenic meromixis results when an external event brings salt water into a freshwater lake, or fresh water into a saline lake. A superficial layer of less dense, less saline water overlies a monimolimnion of saline, denser water. Such situations are mainly found along marine coastal regions where intrusion of salt water occur. A stricter definition of ectogenic meromictic lakes includes only those that are isolated from marine influxes of water. Such isolation may be recent or long-standing. An example of the latter is the southern Norwegian Lake Toke, which most likely has been permanently meromictic for about 6,000 years. The isolation of the lake probably took place during a period when the former fjord depression and the surrounding land were elevated some 60 meters above sea level. The paleohistory of meromictic ice-covered ice lake in Antarctica is similar. Lake Sonachi, a volcanic crater lake in Kenya, has periodic changes in specific conductance due to alternating multi-year periods of drought followed by periods with increased rainfall. Ectogenic meromixis is maintained by the freshening of the upper layer by rainfall and increased specific conductance of the deeper waters, presumably by the increased flow of groundwater which dissolved evaporates. An interesting variant of ectogenic meromixis is found in saline lakes of arid regions or in small depressions that occasionally receive saltwater intrusion. Often these saline lakes overlie deposits of soluble salts such as magnesium sulfate and are only a few meters in depth. The input of fresh water, either naturally during wet periods or artificially as a result of increased irrigation of nearby land, creates meromictic stratification. Whatever the cause of meromixis, some lakes have marked differences in temperature with depth, in which the chemocline is functioning as a heat trap of solar energy. So why don't we look at these figures here? So the first one is figure 7-39. Water temperature at depth of 0, 1, 2, and 3 in Yuanyang Lake, Taiwan, for periods between 2004 and 2005. Temperatures cool appreciably and stratification is usually diminished or lost when large inflow events occur and displace lake water. These results from increased precipitation as indicated by vertical black bars. Downward arrows indicate typhoons that cause mixing, and the X indicates a typhoon that did not cause mixing. Okay. So let's see here. So we have the x-axis, we have the dates, the time, and then on the y-axis here we have the water temperature, and then on the y-axis here we have the precipitation, and then we have the different depth at which the temperature change was monitored. And so therefore, like the dashed one is 0 meters. And so it would be very likely in the higher. So this is at 0 meters. This is at the surface. This is at 1 meter, 2 meters, and 3 meters. And as they were saying, here we have vertical black bars for increased precipitation events. So here we have a precipitation event, and we can see the collapse of the thermocline right afterwards, right? And then as well, they are saying in here that downward arrows and the X. So the X indicates a typhoon, and so there's a typhoon that did not cause actually a collapse of the thermocline for some reason. And so that's one. And then here we have precipitation here. So this is different time periods. So this is in 2004 and this is in 2005. So therefore this is the precipitation rate. So we have precipitation events. We have let's see, downward arrows indicate typhoon that cause the mixing. So these are like typhoons that cause a mixing here. And so in some cases the typhoon doesn't cause a mixing where it's an X. And yeah, and then we have precipitation event that also collapses the thermocline. Okay, next one is figure 7-40. 30-hour record of water column temperature in geothermal Lake Rotowaro in North Island, on the North Island in New Zealand. The water column mixes at night due to the combination of heat loss at the surface, differential cooling, and convective mixing induced by the upward rise of warmer, less dense water. Note, warmer water at 9-meter depth. It stratifies during the day from incoming solar radiation. So here we have the local hours, and beginning in 13 December 2008, and then the depth, and then on the right side we have the temperature. So they are talking about the fact that we have like this contribution of warmer, less dense water that is coming in from the springs, for like the combination of heat loss and the surface differential and convective mixing, and just by the upward rise of warmer, less dense water right here. That's what they're like referring to. And then we have a very good resolution of a thermocline during the day, and as well as here, and then the collapse of it in the middle of the night. Okay. Such heliothermic lakes contain a solar-heated stratum of warm saline water beneath a surface layer of cooler, less saline water. Much of the sunlight that penetrates the chemocline is transformed to heat and retained due to increases in solute concentration at the depth of heating. As a result, temperatures rise within the chemocline. The corresponding changes in the distribution of oxygen and nutrients, as in Ice Lake, Antarctica, create habitats favorable for different species of microbes. A striking example of heliothermy is Hot Lake, a shallow 3.5 meter saline body of water occupying a former Epsom salt excavation in north central Washington. Solar radiation energy passing through the overlying mixolimnion of fresh water accumulated as heat in the chemolimnion and monolimnion, where circulation was absent. The resulting temperature can be in excess of 50 degrees centigrade, and even when the surface of the lake is frozen, a temperature of nearly 30 degrees centigrade can be found at a depth of 2 meters. These dicothermic conditions, in which the monolimnion is considerably warmer than the overlying water of the chemolimnion, are observed in shallow meromictic lakes. Cranogenic meromixis is a type of ectogenic meromixis that results when submerged saline springs deliver dense water to deep portions of lake basins. The saline water displaces the water of the mixolimnion. The chemolimnion stabilizes at a depth related to the rate of influx, density differences, and the degree of wind mixing of the mixolimnion. Meromictic lakes of these types occur in, for example, interior Alaska, where subsurface springs introduce saline water into small deep lakes originating in thawed craters or pingos. Pingos are formed when water rising by hydraulic pressure through gaps in the permafrost freezes and uplift a mound of ice covered by a layer of alluvium. So we already looked at that term, the pingo term, before in a preceding chapter. The overburden usually ruptures, and the ice of the depression can thaw to form small lakes. In some cases, geothermal and saline waters form complex stratification patterns with warm saline waters underlying cooler waters, biogenic or endogenic meromixis. Results from an accumulation of solutes in the monolimnion, often liberated by the decomposition of organic matter in the sediments or water column. Often biogenic meromixis is initiated when abnormal meteorological conditions present the circulation of a normally dimictic or monomictic lake prevent. Morphological meromixis results when mixing from wind and cooling cannot penetrate the full depth of a lake. Over time, solutes may accumulate in the monolimnion, but the resulting chemoclines would not necessarily be sufficient to preclude mixing in a shallower lake. Temperature inversion can occur in the monolimnion. Elevated temperatures observed in the chemolimnion may result from the absorption of solar radiation by dense bacterial plates that occur at that level. Residual warmer waters from the lake period of mixing or geothermal heating. Nearly all deep lakes in the equatorial tropics are meromictic. Some of these are small crater lakes in which sheltering from winds precludes deep mixing. Notorious among these are Lake Nyos and Nonun in Cameroon. With the long period of meromixis and the interaction of groundwater with magmatically produced CO2, concentration of CO2 became high in the monolimnion. At Lake Nyos, a landslide disrupted the stratification and led to the venting of the dissolved gases, and as CO2 has a higher density than ambient air, the formation of a plume of CO2-enriched air that flowed downslope and suffocated villagers of towns below the lake resulted in a loss of 1,746 lives on 21 August 1986. The hazard has since been reduced somewhat with siphon systems that vent the CO2 to the atmosphere. Tectonically formed Lake Malawi, Tanganyika, and Kivu in East Africa are meromictic, with depth exceeding 500 meters and reaching 1,460 meters in Lake Tanganyika. The enhanced mixing during the southeast monsoon causes deepening to only 150 meters in Malawi and Tanganyika, and with lower winds to 50 or 60 meters in Lake Kivu. Sediment cores from these lakes indicate that the lakes have undergone periods of mono and meromixes over geologic time, with monomixes prevailing during dry, windy periods when the lakes were shallower than today, and meromixes during wetter periods as now. Stratification in Lake Kivu, the Democratic Republic of the Congo, Rwanda, results from the interaction of freshwater inputs in the upper layer, combined with incoming solutes from geothermal springs and decomposition in the lower water column. The first chemocline is set by the depth of mixing during the southeast monsoon. Above it, the water column is oxygenated during the monsoon. The other chemoclines occur at depth where subterranean springs introduce water, some of which is CO2 saturated and solute rich. Thermoclines often occur with the chemoclines, as do large gradients in CO2 and CH4, methane. The methane from the lake is currently being extracted and used for the production of electricity for Rwanda and neighboring country. The extraction is designed to preclude the partial pressure of the gases from reaching saturation, which should avoid a catastrophic release as in the two lakes in Cameroon. As natural processes can induce such events, the lake is being carefully monitored. Another quite different cause of endogenic meromixes apparently occurs as a result of precipitation of salt in the upper water strata by freezing out from the surface ice layer. The precipitating salts may accumulate in deeper waters in sufficient concentration to cause meromixes. In Algal Lake, Antarctica, this condition has been termed cryogenic meromixes. Human activities can lead to meromixes. For example, creating a connecting channel between a freshwater lake and the sea for purposes of navigation can result in an intrusion of saline water into the lake and meromixes. The runoff from street de-icing has increased salt concentration in the deeper water of small lakes, resulting in meromixes. The increased solutes have led to delays in spring mixing in larger lakes, with the potential to lead to meromixes. Mining voids, that is, pits where mining occurred, are common in several areas of the world. These initially fill with saline groundwater, but gradually become overlain by a freshwater layer, either from runoff or artificial diversion, such that meromixes results. So before we move on, let's look at these figures here. So figure 7-41, time series temperatures from the southern basin of Lake Tanganyika to 300 meters. Rather than mixing to the bottom, the upwelling and mixing are constrained to the surface, 100 to 175 meters during the dry, windy conditions of the southeast monsoon, May through August. The lake subsequently restratifying in the upper 100 meters. Large amplitude internal waves are evident below 100 meters. So here what they're saying is that, so we have the depth on the x-axis, the y-axis we have the time, so this is between May 1995 and November 1986. And here is a legend for the different colored temperature other terms. So what they're saying is that during the time period between, let's say, November here, so March, we have the development, so March right here, 1996. We have, so rather than mixing to the bottom, the upwelling and mixing are constrained to the surface. During the dry, windy condition of the southeast monsoon, the lake subsequently re-stratify in the upper 100 meters. So here we have the monsoon events, so we have a lack of stratification, and then we have the dry season with the presence of stratification during that time. And then potentially here we have no data. And this is a figure that shows the stratification of temperature, oxygen, salinity, methane, and carbon dioxide in Lake Kivu. So depth is on the y-axis. We have the salinity in grams per liter on the x-axis, and oxygen concentration in milligrams per liter, and then the temperature, and then the gas concentration in moles per liter. So let's see. So therefore, like with depth, with increasing depth, we have increasing temperature as well as increasing concentration for methane, or for all the gases for that matter. The salinity increases from left to right, so therefore these samples here are more saline than this sample here. And then let's see, so we have the temperature profile right here, and so we therefore have like a thermocline that develops right here at the surface, and then we don't have any thermocline here. We have another thermocline right here, which is likely like your seasonal thermocline, and then we have then the temperature pretty much stabilizing, but increasing with depth, which is counterintuitive. It's not usually the case. I mean, I said unless the lake surface is frozen, of course. Whenever you looked at that. Okay. So I think that's going to do it for today, and then tomorrow we'll be looking at oligo mixes, and we'll probably be closing this chapter. So looking forward to it, and we'll talk to you soon. Thank you. Bye.